Welcome to today's class. In today's class, we'll be looking at the application of finite difference approximation to a simple pressure equation. Let's say we have this equation as our simple pressure equation. Recall from our finite approximation, we said that from forward derivative, we said that the f all over the x is approximately equal to f of xi plus 1 minus f of xi divided by h for the first order from forward difference approximation. And also from forward difference approximation for second order, the relationship between forward difference approximation and Taylor series for second order, we said that it is approximately equal to f of xi plus 1 minus 2f of xi plus f of xi minus 1, then divided by h squared. Now let's see how we can apply this our finite difference approximation for forward difference and backward difference to a simple pressure equation. So now recall that this is our simple pressure equation. We said that the P dt is equal to K all over phi mu C times d square P all over the x square. K here, K over phi mu is a diffusivity constant. Let's replace K over phi mu by delta H. All right. So we can simply say that our K divided by phi mu C is equal to delta H, which is diffusivity constant. Assuming that our K over phi mu C is equal to delta H equal to 1, right? Assuming that this is equal to delta H equal to 1, our pressure equation becomes dP divided by dt will be equal to what? Remember that we said that this thing is equal to 1. So everything here becomes 1. 1 times the square P over the x square will give us what? The square P all over the x square. Since we have this, the next step now is to compare our dP over dt to the first forward finite difference approximation equation. If you compare dP over dt, all right, to this finite difference approximation for first order, you can simply say that, okay, this is the f dx. So in this case now, our f, if you compare these two, you can simply say that f becomes what? Your p, and your x becomes what? T. So you can simply say that this equation can also be written as dP, in terms of pressure, it will be dP divided by what? X, but here it is in terms of T. So instead of X, I'm going to have T, will be approximately, remember, we are trying to relate the first order finite difference equation with this. So we can simply say that this is this, it will be approximately equal to, if you want to write it in terms of pressure, we already said that F here becomes what? P. So here will become what? This F becomes what? P I. This will be P I, then this is I plus 1. But now, since we are replacing it in terms of what? Since we are in terms of time, right? We are going to replace this I plus 1 in terms of our n, which is our time level. So this now becomes n plus 1. Instead of I plus 1, we write it as what? N plus 1, then minus our F here, Pi. Instead of I here, so if here is n plus 1, if n plus 1 is like I plus 1, xi will be what? P raised to the power of what? N. So here will be n divided by, our h here now will be delta t. The reason why we use approximation sign here and use approximation sign here is because we have what? Truncated the error from Taylor series. Since we truncated the error, instead of using the equal to sign, we change it to what? Approximation sign. So this will be this. Then also compare our d square P over the x square to this second equation, to the second order finite forward difference equation. If you compare it, you are going to have d square P divided by the x square will also be equal to, In place of this will be what? Of okay. This is xi plus 1, right? So here will be I plus 1. Now, the reason why we use I plus 1, because remember, this one is time, and time has to deal with what? Time level. Now, when it comes to x here, x has to deal with what? The location in what? In space. So instead of using n here now, here will become I plus 1. Then minus 2pi plus pi minus 1. If that is the case, what will be the time level? What will be the time level here, and what will be the time level? The time level for these three pressures now becomes unknown, because we are talking about a location in space that we don't know what the time level. So the time level for this pressure and this pressure here becomes unknown. If that is the case, okay, remember this equation is approximately, so this is approximately equal to this. If that is the case, we are going to substitute dp over dt as this into this equation, and also substitute the square p over the s square. Okay, this is divided by h square. There will be delta x square. I'm going to substitute the square p over the x square as this now into this equation. So substitute dp dt, which is equal to this, into this equation, and substitute the square p over the s square, which is this, into this, then this as this into this. If that is the case, what is our dp dt? Our dp dt is approximately equal to that. So we are going to have this will give us pi n plus 1 minus pin divided by delta t will be approximately equal to the square p over the s square, right? Which is equal to this. This is pi plus 1 minus 2pi plus pi minus 1. Remember, we don't know the time level for this partial derivative. So everything here divided by what? Delta x squared. If you look at this equation uses equal to, but in this equation we use approximate sign. We use approximate sign because we said that the p dt is approximately what? Equal to this, and the square p over the s square is approximately equal to this. So that's why we change this equal to sign now to what? Approximation sign, because the two equations are what? Approximate equations. So we change this thing to approximation sign. Now, since at the right hand side, we don't know the time level. We don't know this. We don't know the time level for the partial derivatives. So how do you get the time level? For you to get the time level now, we can simply assume, the time level as, for this partial derivative as n. And also, we can also assume this as, we can assume as n, and also assume as n plus 1. We can assume this thing here as n, just like we have n here. We can simply say the time level here is n, here is n, here is n. And also, we can simply say that the time level here is n plus 1, just like this, n plus 1, n plus 1, and n plus 1. But in this case now, if you want to assume the time level as n, you use the method called the explicit what? Method. If you assume time level as n, you are going to use the explicit method. And if you assume the time level as n plus 1, you are going to use the implicit method. Assume time level as n, you use explicit method. Assume time level as n plus 1, you use what? Implicit method. So in this class, we are going to look at both the explicit method and the implicit method. So first of all, let's look at the explicit method. Now, for the explicit method, we have to assume that the time level here is what? N, N, and what? N. If that is the case, this our equation becomes P I n plus 1 minus P I n divided by delta t is approximately Pi plus 1 raised to the power of n minus 2 Pi power of n plus Pi minus 1 power of n divided by delta x square. Now we use n now because we assume that the time level is what? N, which is the what? Explicit what? Method. So since we do that, we know that this is Pn plus 1. Pn plus 1 is the unknown pressure. Then Pi plus 1 is the known pressure. This one is also known pressure. No, it's also known pressure. So the ones that have power of n are the known, while the ones that have n plus 1 are the what? Unknown. Since this one has n, and this one is the only one that have n plus 1, it means that it is only Pi n plus 1 that is what? Unknown pressure in this equation. If that is the case, how do we get the value of the unknown pressure? We have to make the unknown pressure now subject of what? Formula. So, and our unknown pressure here is Pi n plus 1. So let's make Pi n plus 1 subject of formula. To make this subject of formula, we have to multiply through by what? Delta t. If you multiply the left hand side by delta t will cancel out. Then here we are going to have delta t over delta s square. So we are going to have something like this. Pi